The Ashokan Reservoir, located at the eastern edge of New York's Catskill Mountains, is majestic. Beyond its beauty, it's also a critical piece of infrastructure, serving as the largest drinking water source for 8.8 million people living in New York City, and an additional 1 million people living north of the city. The impressive abundance of water, nearly 125 billion gallons at its peak capacity, is fed into it by over 459 miles of streams that wind their way down through the surrounding area of the Catskills. The land gathering and channeling this water is known as a watershed. Hello, my friends. I'm coming to you today to talk a little bit about watersheds and river systems, specifically the Ashokan Reservoir watershed and the Esopus Creek drainage system that feeds it. In order to get a really good sense of how they relate to each other, we're going to have to go on a bit of an adventure. We'll start about 24 miles upstream, all the way at the source of the Esopus Creek, Winnesook Lake, and follow the stream all the way down here to the Ashokan Reservoir behind me. But before we start, I want to take a moment to talk a little bit more about how a watershed works. A really simple way to think of a watershed is to imagine a large bowl, and any liquid that flows or drains down the side of the bowl contributes liquid to the puddle that sits at the bottom of the bowl. Now I'd like you to think of that puddle of liquid at the bottom of your bowl as a large body of water. In a watershed, that can be a lake or a reservoir or an ocean. And the liquid flowing down the sides of the bowl can be thought of as the streams feeding that larger body of water. Any liquid that falls within the bowl, which would be precipitation, will eventually drain through streams to the water body at the bottom. So you can think of the edge of your bowl as the watershed divide or the watershed boundary. In real life, this could be the mountain slopes surrounding this particular body of water. So what happens to water that falls outside of this boundary? It goes into a different watershed. Now the whole world can be broken up into these watersheds, and these watersheds can be broken up into even smaller watersheds. I like to think of those stackable dolls. So any rain or snow melt within this boundary will drain to this body of water. Any rain or snow melt on the other side of the boundary will feed the other body of water. While exploring a watershed, you can use your imagination to visualize the shape of your watershed by looking up at the mountains and using your imagination to connect all the points of high elevation to define your watershed boundary. So the receiving body of water here is the Ashokan Reservoir, and the Ashokan Reservoir watershed covers 255 square miles of land, meaning that any water that falls within that 255 square miles feeds the Ashokan Reservoir. The largest contributor to the reservoir is the Esopus Creek. The Esopus River system is known as a dendritic river system. The word dendritic means that it has a branched form that resembles a tree. So you can think of the Esopus Creek's main channel as the trunk of a tree, and each of the tributaries as the limbs or branches of that tree. All in all, the Esopus and its 9 major tributaries make up about 300 miles of the 459 miles that feed the reservoir. Those streams are part of the Esopus Creek's river or drainage system. The place where the main river in a river system begins is known as the river's source or the river's headwaters. Those headwater streams are higher in elevation than the receiving bodies of water, and they collect more water and more sediment from tributaries as they move through the steep valley to the lower elevations and flatter ground, before finally reaching us at the bottom of the bowl here at the Ashokan Reservoir. Now, here's where it gets interesting. Each of these tributaries has their own specific amount of land that feed them water, so they have their own watersheds. These are all sub-watersheds of the larger Ashokan Reservoir watershed. So when the two streams meet, those watersheds can be added together to create a larger watershed feeding water to that point. you start to get a sense of how all of these water bodies affect one another. The water literally and figuratively cascades down, merging together and inheriting all sorts of variables from one another along the way. I really think the best way to understand the scale of this system is to see it for ourselves. So we're going to take a trip up to the headwaters now, and then we'll make our way back down by tracing the Esopus Creek and stopping at the confluence of each of the 9 major tributaries along the way. We're going to be noting the expanding size of the watershed, as well as changes in the channel width, or the hydraulic geometry, as well as changes in geography and geology. Let's go. Here we are at Winnesook Lake, technically the source of the Esopus Creek headwaters. We are about 2,700 feet above sea level at this point, and there are about 0.1 square miles of land draining into this lake. So while many people do consider this the source of the Esopus Creek, this also does have its own watershed. Water is draining from the surrounding hills through springs and runoff. So here it is, all of the water leaving Winnesook Lake and heading toward Esopus Creek. It's going to continue down this way through this small stream channel and end up at our next stop, the first major tributary to Esopus Creek, Birch Creek. It really makes you think about how small things can have large impacts, and how a watershed is really a sum of all the small parts that come together. As we continue down the stream channel of the Esopus Creek headwaters, we meet our first significant tributary about 1 mile downstream. This unnamed tributary nearly doubles the size of our drainage area, bringing it from 0.64 square miles to 1.18 square miles. We're now about 6 miles downstream of our first significant tributary, and our watershed is about 16 square miles in size. You really see the valley open up here, but also take notice of how much sediment is here. We have very large deposits of cobbles, and the stream at this point in the valley bottom with a large amount of sediment will start to move back and forth and create a braided drainage pattern. Here we can start to see some examples of that braided stream pattern that I mentioned before. Our main stream channel is off through the woods to the left over there, but we have water flowing through this channel here. And then we also have some dry stream channels off to the side, which will be flowing with water during higher flows after rain events. And those occur all throughout this forested area. We have arrived at Birch Creek. Birch Creek is an 8-mile stream. It adds 12.8 square miles to our watershed. Here, the Esopus Creek headwaters transitions to the main stem, Esopus Creek. We have these long sections of deeper water and our shorter riffles. Makes for really great habitat for our trout. Makes for a great spot to come fishing. Now we're gonna head on back to the truck and drive to our next location. So just wanted to stop as we are walking up to the Bushnellsville Creek confluence just upstream of here to show how the Esopus Creek is accessing its floodplain in this area. We're about 4 feet above the current water surface, but you can see by the way that these trees have been pushed by floodwaters that the water does come up this high and come this far out by the way that they are leaning and pointing in the downstream direction. So I always love to stop and take a moment to look at the rocks that are lined up along the stream's floodplain, this cobble bar here as I'm walking along. You can tell that these rocks were deposited by flowing water by this angle, this pattern that they make called imbrication. This imbricated pattern is this slanted pattern that you're seeing here, where the top end of the rocks is facing downstream. Okay, here we are at Bushnellsville Creek. This small stream behind me is about 6.5 miles long. It's fed by about 11 square miles of land, bringing our total watershed size to about 59 square miles. Down here, the Esopus Creek really starts to wander across the valley bottom, coming around this bend and making a tight turn to the east. We're now coming up on the first of our 3 smallish tributaries out of our 9 major tributaries to the Esopus Creek. The stream here is now going back and forth under roads and crossing under the major highway here. So over here is Fox Hollow. This stream is only about 3.7 miles long with about 4 square miles of land feeding it. But you can really see how this small stream has enough power to carry a lot of sediment by observing the cobbles and boulders that have piled up at the mouth of it. Now we can go take a look at Peck Hollow and see how that compares. Here we are now at Peck Hollow Creek, just downstream of Fox Hollow. As I mentioned before, these 3 tributaries that we're going to talk about in this zone are all pretty small. Peck Hollow is about 5 miles long with a drainage area of about 5 square miles. But once again, we see that it has the ability to carry large amounts of sediment and we observe this by checking out the cobbles and boulders that have piled up at the mouth of the stream. In this stream though, it also forms this kind of step pool pattern as it approaches the confluence where it cascades into the Esopus Creek. While I'm here, I just want to take a moment to point out these plants that are growing here. This is actually known as Japanese knotweed. It's a non-native plant that we see growing a lot around our stream banks. This one in particular is of interest because it has the ability to outcompete other native plant material and take over the entire stream bank. So this can actually destabilize our stream banks, causing more erosion, which shapes our channel but also impacts the quality of our water. Here we are at Broad Street Hollow, the last in our series of 3 small tributaries. This one is actually the largest of those 3 with a drainage area of 9.5 square miles, bringing our total drainage basin to an area of 79.2 square miles. You can see that this is a larger drainage area than the other small tributaries by how wide the channel is here compared to those other 2. Now we're going to head to Woodland Valley where the channel size will grow even larger. Okay, we have arrived at Woodland Valley Creek. We're standing right above the Woodland Valley Esopus Creek confluence. You can see Esopus Creek flowing behind me. And there's quite a bit of water moving through the system right now. So while our stream here, the Woodland Valley Creek, is only about 3.5 miles longer than Broad Street Hollow, it's fed by about double the drainage area of Broad Street Hollow at about 20.5 square miles. Okay, so what I've found here is some of this red clay that is pretty typical of our superficial geology throughout the Catskills. This clay was actually deposited during the last ice age when the glaciers were retreating and melting off. It's usually underground, but there are places where it does become exposed, and during higher flows, the water's energy is able to break the bonds between the clay particles and release them into the water, where they stay suspended and add turbidity to the water. So the term turbidity refers to the cloudiness of the water. This cloudiness is related to the amount of fine clay particles that stay suspended in the water column. Okay, here we are at Stony Clove Creek. This is our largest tributary to the Esopus Creek with a drainage basin of 32 square miles, bringing our total drainage area to 138 square miles. The Stony Clove is fed by steep, high-energy streams, but here at the confluence with the Esopus Creek, the valley widens and the slope of the creek decreases. Okay, so here we've reached the beaver kill. We're now about the same elevation that we started out at the Ashokan Reservoir. And this sub-watershed is adding another 24.9 square miles of drainage area to the overall Esopus Creek watershed. And we just have one last stop before we reach the reservoir again. We'll be stopping downstream at the Little Beaver Kill. Here we have our final tributary, Little Beaver Kill. After Little Beaver Kill passes under Route 28 here through this culvert, it will add 16.7 square miles of drainage area to our overall watershed. We've had a long day, but we are almost at the end of our adventure. We're just a straight shot to the mouth of the Esopus Creek at the Ashokan Reservoir. Okay, so we've finally reached the end of our adventure. We've made it back to where we started, the Ashokan Reservoir. We've come all the way from Winnesook Lake, where the water trickled through that small culvert down that steep mountain channel, all the way down to the valley floor where it winds back and forth before it meets the reservoir. We've observed changes in channel geometry, channel width, channel velocity, the kind of sediment that the stream is carrying, and the type of land that the water is flowing through. So while our journey may be over, the journey for the Esopus Creek is far from over. Once it leaves the reservoir through the dam downstream, it'll travel to the Hudson River, where it'll then end up in the Atlantic Ocean. So whether you're a scientist who studies river systems or just someone who loves to be outdoors, understanding watersheds and how they work is important for everybody, because through watersheds, all landscapes are connected.